Alright, now what we want to do is look at how radicals work, how we do radical arithmetic. So for example, if I have the square root of 2 times the square root of 3, what would that be in terms of a radical? Okay, I mean, you might say, well, question, is that the square root of 6? Well, just to get us started, the one way to find that out is just to type each side in. So let's type in the square root of 2 multiplied by the square root of 3, and the decimal we get is 2.449. Now remember, this number goes on forever. These are irrational numbers, so the pattern never ends and the number never ends. And the question is, does that equal the square root of 6? Seems to be. So 2.45 on both sides approximately, on and on and on. That seems to be true. Okay? What if we were dealing with cube roots? So once again, we might hypothesize that the answer to this might be the cube root of 6. So let's go off to our calculator to see our cube root button. Our decimal approximation, 1.82, and the question is, does that equal the cube root of 6? Yes, it does. So it seems as though our theory that we multiply the radicands is true. Okay. Now in both of these examples, you'll notice that our indexes were the same. In this case, an index of 3, up here an index of 2, because they were square roots. Let's see what happens when the indexes are not the same. So let's see what happens with this example. What might the answer be? Well, possibly if we multiply the radicands to get 6, what would we do with the indexes? Add them, similar to what we do with exponents, or multiply them. Okay, 7th root, 12th root, not sure. Okay, these are both reasonable hypotheses. Question mark. We don't know if this is true, so we're going to go off to our calculator and see what happens. So we have the cube root of 2 multiplied by the 4th root of 3 gives us this decimal approximation. Alright, if we do the 7th root of 6, that gives us something different. Okay? What about the 12th root of 6? That also gives us something different. So what we're seeing here is that this does not equal these results. So at the moment, all we can seem to conclude is that if the indexes are the same, we can multiply the radicands. If the indexes are different, we have no shortcut for doing that. So our bottom line is, to multiply radicals, the indexes must be the same. The indexes are the same. If the indexes are the same, then you multiply the radicands, and we can express that as so. What we want to do now is take the idea we've just talked about and apply that to simplifying radicals, putting radicals in simplest form. And the definition of that is that there can be no perfect square roots or cube roots or 4th roots under the radical sign, depending on which type of radical we're dealing with. So in the example I've got here, the square root of 12, I'm dealing with square roots. What I need to think about is whether or not there are any perfect squares that divide into 12. And if I think about that, I come up with the square root of 4. Now, because of what we just talked about, we could rewrite this expression as the multiplication of two radicals with the square root index. Square root of 4 times the square root of 3. And what we're doing here is that this now breaks down to a rational number. The square root of 4 is 2. The square root of 3 is still an irrational number, so we're going to write it like this. And so what we're saying is that the square root of 12, which we call an entire radical, is equal to 2 multiplied by the square root of 3, which we call a mixed radical. because this number is made up of a rational number multiplied by an irrational number. Okay, if you're not convinced, let's just rush over to the calculator and let's type in the square root of 12. And now let's multiply 2 multiplied by the square root of 3. And you'll see we get equivalent decimals. Okay, another example, let's take the square root of 48. So again, you want to think about the largest perfect square that divides into 48. And if you think about that for a moment, you come up with the square root of 16 multiplied by the square root of 3. Square root of 16 is 4. The square root of 3 isn't a perfect square, so we keep it as square root of 3. So square root 48 is equal to 4 times the square root of 3. We can do this simplification process with any index. So let's take the cube root of 24. Now this time I would be thinking of the largest perfect cube that divides into 24. Keeping in mind that my perfect cubes are 1, 8, 27. They get big pretty fast. So far, do any of these numbers divide into 24? Well, 8 does. So I can break this up as the multiplication of two radicals with the same index, the cube root of 8 times the cube root of 3. And the cube root of 8 is perfectly 2, and the cube root of 3 stays the way it is. So this is the same as this, and you can confirm that with your calculator.